So first of all, thank you everyone for joining this talk. My name is Navneet. I'm a senior software engineer in AWS, and I'm also one of the maintainers of the KNN plugin in OpenSearch. With me,
Hey everyone, my name is Jay. Also work at AWS, and I'm one of the maintainers of the OpenSearch core.
Yeah. So today's talk will be about how the GPU-based index acceleration, one of the OpenSearch new frontier. So we'll talk about, so in terms of agenda, we have a lot of things to go through. So first we'll talk about the vector index architecture, how, and at least you would have seen in the last talk which was given by Vamshi in terms of how a vector index is structured, what a vector is. We'll go through it on a high level pretty quickly. We'll talk about why do, in today's world or in today's time, why do we need for faster index builds. It has been touched upon by in the keynote by Corey, and also Vamshi was talking about it. We'll go through it one more time. We'll talk about what were the indexing improvements that we have done in 2024, and then we'll directly jump onto our remote GPU-based index architecture. We'll dive deep into some of the core concepts. We'll go through how you can set up this overall architecture and how all the services works. Okay. With this, let's start. So let's first talk about some of the ABCs of the vector index. As you know, like within OpenSearch, you have an OpenSearch index. So if you look closely, a vector index is nothing but an OpenSearch index. And within an OpenSearch index, you have shards. Shards are nothing but a Lucene index. Within shards, you have a lot of segments. You can have like one to many segments present in per shard. Within those shards, you have basically different types of file which stores the different data structures. So you have DVD files which store your doc values. You have your TIM and TIP files which stores the frequency, or sorry, the terms dictionary. Similar to this, for a vector index, we have another file which we have added within the segment which stores the vector data structure. Okay. For OpenSearch, we have like different engines, and one of that engine or one of that specific vector engine is FIES. For that engine, we have a specific file called as .FIES, which stores the FIES related data structure. And as you have seen in the older, in the evolution to trillion scale vector database, you see that we had like HNSW index or HNSW as an algorithm for doing vector search. We have IVF. So all that information gets stored basically within this file. Okay. In a serialized way, and whenever the search is happening, what we are going ahead and doing is we go through segment by segment, we read these files, perform a k-nearest neighbor search on top of it, and then return those back to the coordinator node. Okay, so that's the high level vector index architecture. A key point to take over, to keep in mind over here is, I've heard so many times talking to different people, hey, is a vector index separate than a regular OpenSearch index? Can I do same operations? Can I do filtering? Can I do aggregations on top of it? And the answer to all those queries is yes. So a vector index is nothing, as you can see in the diagram, it's just like a plain OpenSearch index. The important part to note in a vector index is you have a couple of things. You have first index setting that defines that, hey, this is an OpenSearch vector index. The second main important thing over there is you have a field type, which is a vector field. You define that, hey, this is a KNN vector field. First, you have the field name, just like similar to any text field. Then you have a type, which is the KNN vector. Then you specify that, hey, this vector would be of dimension 8, 128. You can go up to 16K, if I'm not wrong. And then you define the space type or the vector similarity function, which can be inner product, cosine similarity, or L2. And I think we have gone through this in the last two sessions, so I'm not going to bore you about, hey, what is a vector similarity and what other things are. But this is a basic index structure. Okay. Now, let's talk about, with the evolution of vector search in the past couple of years, we are seeing more and more use cases coming up. We recently had a talk about trillion scale vector database. So let's talk about why do we need faster index builds. Okay, I cannot just sit for like 2 days or 3 days just to get a trillion vectors ingested into my index. Why there is a necessity to build the faster indices. So first of all, the main important thing is the scale is moving from billions to trillions. So as that scale moves to trillions, the time it takes to build an index is going through days instead of hours. And if you have to wait for an index, or if you have to wait for doing a single query for like weeks or maybe days, it's not a good experience. The second thing which we are seeing, at least in terms of customer experience, is people are trying to rebuild the whole index again. They are doing daily jobs, they are doing maybe weekly jobs to rebuild the whole index. And one of the reasons, at least we have identified or we have seen customers or users doing this thing, is they are changing their models. They are not happy with one model. After a certain point in time, they want to change it. Okay, or they went ahead and actually improved their own model. So they want to rebuild that whole index again so that they can get better search quality. And that's where if you have to rebuild your whole index again, and let's say you have billions or trillions of vectors, it's not feasible to like just wait for 4 days or 5 days to have a completely or to have a full index built. And the next thing which has been again touched upon is people are moving from lexical search to semantic search or multimodal searches, where I have consider a use case where in production, I have, let's say, billions of documents which are ingested from an e-commerce use case standpoint. And now I want to enable a semantic search on top of it. Okay, it's a fully production running cluster. I want to showcase quickly that, hey, this is working or not. Or even if I have to rebuild, or even if I have to convert my semantic search index to a vector index, how do I do it? And that's where having a faster index build will help you. You want to try out multiple models, you want to try out different configuration, and that's where faster index builds help. Another thing is tuning the index. As mentioned in first talk by Corey also, that vector indices are not simple index. You have to tune it to get the desired performance, to get the desired recall. And to do that, you have to build multiple indices. And you can do it in a simpler fashion where like, okay, I have billions of vectors, but I don't want to build a billion index. I can just go with a million index, or I'll take a subset of vectors, build an index, and see if my performance is working well or not. But as we all know that as you move to larger scale, those assumptions doesn't hold true. And that's where you want to build faster billion scale or trillion scale indices to basically figure out, hey, whether this hyperparameter is working correctly or not, whether this type of model is working correctly for me or not. And that's where having a faster index builds can basically accelerate these processes. Okay. Now, moving on, so I'll not go beyond 2024 because as we have discussed in the last talk, before 2024, there was not like a urgent need of billions of vectors, but within 2024, we started seeing a lot of need for billions of vectors, and that's where we'll talk about what are the improvements from a core vector engine standpoint we have done in 2024, which actually helps stabilize the indexing. I'm not going to go through the searches. Searches are just a byproduct, at least in my understanding. If you have a good indexing, you can actually do a better search. So the first improvement that we did was we actually improved our memory footprint. So there are like two main features that we have added: streaming vectors to the native memory, and then was the iterative graph builds. So just to give a background, what was happening, at least on the streaming, the first and the second part was, whenever we were in OpenSearch, as you know that the vector files are present at a segment level, and then there are periodical or background merges that happens. So during those merges, what used to happen was we first used to load all the vectors into the heap space and then transfer it to the native memory, which was a big bottleneck for us, because if you try to load vectors which are greater than 30 GB or 32 GB, which was a standard heap size for OpenSearch, it used to crash. Okay, and that's where we added this streaming support, where you will read the vectors from the segment files in a block fashion, and then you move them to the native memory. Okay, and then we added an improvement on top of it, where rather than actually just transferring those vectors and then allowing those vectors to grow in the native memory, we actually went ahead and started doing the iterative graph builds. So the idea over there was, hey, you took a 100 MB chunk of vectors, you first load them into the native memory, build a graph out of it, and then again load another 100 MB chunk, and then ingest those vectors into the already created graph. In this way, you're never going to explode your heap. The pressure on the heap reduces, and also on the native memory, because at once you don't have this huge, I would say, allocation in the memory. Okay, which will obviously helps you reduce the fragmentation, which helps you build the indices faster, and it also helps you put less pressure on search. Okay. The next thing that we introduced was compute improvements. Okay. And if anyone of, I think most of you would have used vector search with OpenSearch, one of the things that you would see during a vector ingestion workload is your CPU spikes very quickly. The moment you start doing ingestion, you'd start to see if you put more pressure on the cluster, the data node CPU utilization starts to become 100%. And the reason for that is because we are building those HNSW structures in the background, and those structures require a lot of compute. Compute in terms of, hey, you're doing distance computation between two vectors, and you have to do thousands of them. And with our experiments, we have seen like it just quickly turns to 100%, which impacts your search, again, in a production running traffic. So that's where we added a support for something known as smarter index builds. So the idea over there is when a segment is getting created, we identify that, hey, is it necessary to build a HNSW structure over there, or can we just live with a brute force? So you just store them flat in a .vec file, which is one of the Lucene file, and you just read through it. Okay, so that was the first thing that we added, and obviously the second thing, which is advanced MD instruction sets that we have added, which includes AVX 512, AVX SPR, which actually improved a lot. Okay, next thing is the storage reduction. Okay, this is like we added a support for something called as derived source. This has been talked by, again, Wamshi in the last session, but let me just touch upon it a little bit for those who haven't attended that talk. So the storage reduction over here basically means earlier what we used to do was whenever you are ingesting a document into OpenSearch, OpenSearch will take your exact document and store it in a Lucene stored field, which we name it as _source. Okay. And that, based on our experiments, what we saw was it was taking 60% of the index size. Now you can always say that, hey, this is disk. Why you are so much caring about the storage? The problem which these larger index size creates is whenever you are doing merges of the segments, which happens again continuously in the background, these files needs to be loaded into the memory to do the merge. Okay, and that actually impacts your indexing performance. So we added a capability called as derived source in it, where rather than storing those vectors into the stored field, we used more optimized fields, which is being stored in .vec, and we use that to basically do all the operations which _source was doing behind the scene. One of that was, hey, if I have to do reindexing, if there's update by query, how do I do all these things? So we ensured that a full compatibility happens with the derived source. Okay. And with that, we were able to see 50 to 60% reduction in the storage. Let's talk about some of the benefits that we got with this. The first benefit, again, with the streaming vectors change and iterative graph builds, we were able to see more stable index builds. So if you see on this side, like left, I hope it's on your left hand side, which is the old, if you see, I'm not sure if you can read it, but it was around 7 GB memory that we were consuming if we are doing the index builds, and once we have applied the fix, the memory just dropped to 4.5 or 4 GB. Okay, that was the native memory, and this is from one of the experiment that if you go to like the second QR code, you will see all these details. That was first. Second, we saw a 50% reduction in the memory consumption, as you can see from these graphs, because we were building the graphs iteratively. So at a certain point in time, you don't need to store 2 copies of vectors in the memory. One which is being taken by HNSW, and another which is by the vectors that you have just loaded into the memory. So that's the second part. With the smarter graph builds, we were seeing a reduction in the index build by 40 to 50%, because the way you have to understand this reduction is when you are ingesting documents into OpenSearch, whether they have vectors or not, you basically create segments in the background. And as you keep on indexing, these segments keep on getting merged. So think of this like you just created a segment, and 5 minutes later it just goes away. There's a new segment gets created. So those are your wasted computes that was happening. And that's where that smarter index build helped. First of all, you don't have to build those smaller graphs for those smaller segments. That's a good benefit, so you can ingest more. Okay. Second thing, during merges, the merges are becoming faster because you have to go through less number of files. So that actually helped us reduce the index builds by 40 to 50%. Another impact of the same, I would say, smarter graph build is faster refresh. Now your read after write consistency is maintained, okay, because you're not creating graphs. If you're not creating graphs, your segments are ready to do the search. So that happens next. And with derived source, you'll see a 60% reduction in the index size. You can see on the right-hand side, this was the time when we launched the feature. There's a huge drop on the index size. I'm not sure if you can read it, but there are links within this presentation to these blogs where you can go ahead and take a deeper look. And as I was talking about, because you are merging less size segments, your force merge or basically merges are becoming faster, okay, which we are able to see. Moving on, the next question arises in someone's mind is, hey, is this enough? I'd say maybe. For some use cases, it can be. If you're just building a million scale vector index, you should be good with all these optimizations. But a good question to ask over here is, can we do better? And since you guys have come to this talk, which is GPU accelerated index build, so the answer would be yes, we can do better. Okay, that's where comes the GPU-based index acceleration. Before we dive into the architecture, let's look back onto the current architecture, or just before this, what was the architecture? So you have your documents which contains vector. You're ingesting into OpenSearch domain or OpenSearch cluster, where you have a data node which acts as a coordinator, which basically partition your vectors into different shards. Shards are nothing but partitions, and they just go ahead and create segments. Okay. Now the new architecture, and that's where we integrated our GPU-based index acceleration. So you go through the same architecture where you have a customer or a user ingesting documents into OpenSearch, but on the right-hand side, we added a completely separate option to add a fleet of GPUs, which we are right now calling it as a remote vector index build fleet or a remote index build service, which you can create of your own. And if you look closely into this remote vector index build, it is nothing but a collection of GPUs which are running, okay. There's an option for object store like S3 or Azure. So the way overall indexing is working right now, if you enable this feature, is you're still ingesting your documents into OpenSearch domain. Okay, it goes to the data node, it goes to the shards. During the segment creation, we are identifying that, hey, whether the GPU-based index acceleration is beneficial or not. If the answer is yes, based on some heuristics, which obviously you can change since it's open source and we allow everyone to change whatever they want. So what this data node or this particular shard is going to do is it will upload all those vectors to a remote store or to an object store like S3 or Azure Blob Store or maybe GCP. And then it will let that remote vector index build service know that, hey, there are vectors which are present on this location. Please build an index for me. Okay, so there, we'll talk about more details in terms of how to enable all these things in the upcoming slides. But the overall idea is this data node talks to this remote vector index build service, say that, hey, this is where my vectors are present. Go ahead and build an index for me. It builds the index. Let the data node know that, hey, your index is built for that segment. Data node goes ahead and downloads it back from the object store and store it along with the same segment. Okay, so this is very much similar to how we were doing it earlier. It's just that the whole process of building the index at the segment level is moved outside. Okay, and using GPUs, you are able to build those indices. You are able to do those merges faster. Okay, now the next question comes up is, hey, what are the benefits of this architecture? Why don't you just put that GPU node inside OpenSearch cluster? That seems a very viable solution. Okay, but when we look closely into the architectural benefits, and if you go to the main RFC also, we have talked about both of these two approaches. The first benefit that I see or we saw with this particular architecture is this is hardware agnostic. Okay, all you need to care about is, hey, there is a fleet or there is an endpoint that can build an index for me. Okay, it doesn't matter what kind of algorithm you are providing behind the scene or what kind of hardware is being used. Second thing is it's cloud agnostic. So You don't have to worry about, hey, do I need to do all this locally? Can I do it cross-cloud or not? Third thing is multi-tenant. So one of the reason, if you see, is if you have put a GPU node or a hardware accelerated system into your OpenSearch cluster, is those nodes are bound to that cluster. But having a separate fleet, or if you can maintain a separate fleet, you can actually pair up multiple OpenSearch domains. So as a provider, I don't have to worry about, hey, if I take this one GPU node, it will increase the cost for the users or for the deployment. And that's where the multi-tenancy comes into place, where you can actually allow different clusters to talk to the same fleet and basically builds the index. The third thing is people can build for pay as you go. So you don't have to keep your GPU machines or these hardware accelerators running for all the time. You can just, like, if I feel that, hey, around like noon or around night, I need to have a heavier indexing, I can just quickly spin up that fleet, okay, or quickly scale up my fleet over there and then just complete my indexing and let that machine go. And that machines can be used for something like ML machine learning algorithms or some other, I would say, semantic search techniques or anything like that. Okay. So these are like 4 core benefits. Apart from this, there are multiple other benefits, but we'll just focus on these 4. Now, let's dive deeper into the main algorithm which is powering this particular indexing acceleration. So behind the scenes, so right now if you look at, and as Corey has also talked about in his talk, is we have enabled this remote GPU-based vector index build fleet uses a CAGRA algorithm to build your vector index. Okay. So what is a CAGRA algorithm? CAGRA or a CAGRA graph. CAGRA builds a fixed degree proximity graph instead of a hierarchical graph just like HNSW. Okay. So if you see what is a proximity graph, a proximity graph is nothing but basically you have a bunch of nodes which are getting connected using some sort of relevance or some sort of mechanism to say that, hey, these 2 nodes are closer to one another. Okay. Which is similar to HNSW, but yeah, there are like more differences that we'll go through. So let's dive into how these graphs are getting constructed with the CAGRA algorithm. So basically in CAGRA, graph construction happens using 3-step process. Okay. The first step is you build an initial KNN graph, which is basically you are saying that, hey, these are my nodes and these are nodes which are closer to this particular node. Okay. And the CAGRA uses basically two graph build algorithm. One is NN descent and another is IVF PQ. Okay, both of them has their own pros and cons. But the main goal of building this graph is we want to just build. We don't want to build a perfect graph. We just want to build a decent graph. Okay, and you'll get to know why that's the case. Because in the next step, what we do is basically we are optimizing those graphs. Or that particular graph which we have created, we keep on optimizing that graph until we are satisfied. Okay. Again, there are more parameters around it, how you can tune these optimization steps, but that's the overall idea. Once that particular optimized graph is created, the third step comes in, and which I feel is another critical step in the whole construction is we build a reverse edge graph. Okay. So the idea over there is, hey, if your node A is connected to node B and B is connected to node C, the reverse graph would be constructed like this, where you will have edges from B to A and C to B. Okay, and the main idea, which at least when I was reading the paper, I was able to identify was during the first 2 steps, it can happen that you have the areas of graph which are not reachable. Okay, since CAGRA is a directed graph, this problem can happen. And the way to solve this thing is you build a reverse edge graph and then merge both of them. In this way, you will finally get a graph which is easily navigable, okay, and you can reach to any parts of the node, any parts of the graph. That's basically completes the CAGRA graph construction. Once this graph is constructed, and as you already know, these graphs are constructed using GPUs, so it totally makes sense that these graphs are only searched using GPUs. So the next step, at least from an OpenSearch standpoint, is how do you allow these graphs which are constructed on GPUs to search on CPU nodes? Okay, because if you see the overall architecture, we were just using our remote index build fleet to do the indexing. We're not using it for doing the search. All the searches are still happening on the CPU nodes. Okay, so the idea over there is CAGRA is providing us the base layer. As we already mentioned that CAGRA is a single layer graph. It's not like a hierarchical structure which we see with HNSW. So you have this base layer. So the idea over there is we need to convert this CAGRA graph into the HNSW. Now, if you know about HNSW, HNSW has some specific parameters like M, EF search, and EF construction. Okay, we'll talk about M only over here because EF construction and EF search are more like dynamic values that you can work with, because M is very important. So M basically defines the number of bidirectional link that you can have. Okay, and the idea which we use and the way we have mapped CAGRA to HNSW is whatever is the graph degree present on the CAGRA, we take a half of it, which acts as an M parameter. Okay, that basically tells you these are the number of bidirectional link. Now, this is the first step we do. The second step is we'll copy the CAGRA graph nodes and its neighbors to build the HNSW base layer. So it's a simple copy where you have like, hey, this node has 4 or 5 neighbors or X number of neighbors, just map them into HNSW data structure properly. And we build the whole base layer. There's an optional step which is added if you go and look into the phase implementation through which we are actually consuming the QVS and the CAGRA implementation, is you can actually build the hierarchical structure also. Okay. But based on our experiments, what we have seen is this actually adds a 30% overhead on your overall graph construction. So that's why I have called it as optional. So the idea is you get the base layer from CAGRA, and then you say that, okay, I have all these nodes which is present in my base layer. I'll start inserting them into the HNSW structure and then build the top layers. Okay, and this is the same way how HNSW also works. HNSW starts by building the base layer, and then it basically, whenever you are adding more nodes, it heuristically identifies that, hey, what nodes I need to move to the top layers. Okay, so that's the third, and then finally we serialize into a format which our data nodes can understand. For us, that format is HNSW 5 index. Okay, now moving on, since we know that for OpenSearch, we have only created the base layer. Okay, now how do we do search on top of it? Because in HNSW, the idea was, hey, you would have a lot of entry points and you'll just go through those entry points from top layers and then you reach the bottom layer. But in the base layer, you have 0 entry points. Like, how do you figure out what is the best entry point? Okay, so the thing that we do is to start the search, we need an entry point. So how do we get the entry points? The idea that we have utilized over there is, okay, we'll pick some random data points from the base layer and we'll use the query vector to identify that, okay, which is the closest entry point, okay, or which is the closest point to this query vector, and we use that as an entry point. What this helps us is, it helps us figure out the part of the graph where I can get the closest neighbor. And if you try to remember like what was happening in HNSW, you are going through the top layers to identify an area in the base layer or the 0th layer to say that where my nearest neighbors can be present. So this is a simpler, I would say a simpler idea that we use to ensure that you can reach onto the base layer and you can reach to the specific area where your closest vectors are present. So yeah, we use that as an entry point to do the search. Now comes the next part, which was more difficult, I would say, which is like, how do you tune these CAGRA parameters? Okay, since if you look from a user interface standpoint, we're not exposing all this information to the customer. And obviously, it's not good to expose all these hyperparameters to the customer. So from the OpenSearch side, we actually started a goal with tuning these CAGRA parameters with a simple goal like, hey, we want to have those parameters which will give us the best recall when compared to CPU at lowest memory footprint and at the best build time, okay, or at the lowest build time. So we did a lot of experiments with, it was just basically going over a matrix of, I would say, matrix of values to figure out what is the optimal value, and we have identified that, okay, this type of parameters will give you the best build time for best recall and the GPU memory. You can read about all these things on the issue QR code that I have attached. basically we plotted some graphs, we identified that, okay, for these values, this works well, okay. That's the overall idea, but the goal was again the same. We want to get a better recall or similar recall when compared to CPU with minimal build time and the memory footprint, okay. So in this way, user don't have to understand that, hey, there's a CAGRA running behind the scene, oh, what should be my default hyperparameters. They can still work with the HNSW parameters and let OpenSearch drive the best recall for those parameters. Now comes the performance results. So we integrated all this integration into OpenSearch, and what we are seeing is we are able to, we are seeing a 9.39x faster index builds. Again, this is a lower bound which we are seeing. Okay, we are seeing in the CPU utilization reduction. If you remember earlier, I was saying like the moment you start indexing, the CPU utilization was shooting up to 100%. We are able to see a 2.5x reduction in CPU. Okay, and then the overall cost, because you are building the index in less number of less time, we are seeing an overall cost reduced by 3.4x. Okay, with this, I'll hand it over to Jay, who will talk about how you can enable GPU-based index acceleration with OpenSearch. Over to you, Jay.
Thanks, Navneet. So Navneet just gave us a ton of really great background on how GPU, or I guess what GPU indexing acceleration is and how it works. I'll talk a little bit more now about how you can get started with it in OpenSearch itself. So first, let's just look again at that architecture diagram that Navneet shared earlier. If you recall, he mentioned that each data node is responsible for uploading the raw vectors to a remote object store, and then also handling the segment build on its own. This raises two questions for us, though. First, when should we actually do this upload? And second, what happens if something goes wrong in our remote index fleet? So let's talk about the first one first. When should we actually use the GPU? Should we upload each vector to the object store as it comes in one by one? Probably not. That would create millions of objects in our remote object store, right? So just like for CPU-based indexing, just like for CPU-based indexing, for GPU indexing, we use the same flush and merge operations as the entry point in. The next question then is, do we do this on every segment? Again, probably not. There's going to be segments that are too small where the object upload into the remote object store just eats away too much for performance improvement. Then on the other side, there's also going to be segments that are too big, and then our actual GPU instance hardware doesn't have enough memory to support it. So in these cases, we want to skip the upload and just not go down the GPU path at all. So if all of our thresholds are satisfied, which I'll talk a little bit more about in just a minute, we go down the GPU path. If not, let's stick with the CPU. Then the second question from the last slide is, what happens if something goes wrong? So for GPU indexing, since we're working with a remote indexing fleet, things can happen in the cloud and it can stop working. So what we do on the OpenSearch side is we ensure that we always fall back to CPU indexing in case of any errors or availability issues. And then finally, that leads to a completed GPU index. So like I said, I'll talk a little bit more about these segment size thresholds and why we need them. First, we have a lower bound to avoid inefficient remote object transfers for small segments. On larger segments, we can afford some of this overhead for doing like an upload of your raw vectors, but for smaller sizes, it doesn't make sense. You'll get the same performance, maybe even worse. By default in OpenSearch, this is a 50 megabyte threshold, but like Navneet said, you can customize this however you like. On the other side, we also have an upper bound to fail fast whenever our hardware won't be able to process our segment size. So for example, if you have a GPU that only has a small amount of GPU memory, then you actually won't even be able to build the graph of a very large segment. In that case, it doesn't make sense for us to try to upload the raw vectors to the remote object store first. Instead, we'll just completely skip it. And again, this is configurable depending on however you have set up your GPU fleet. All right, so then let's talk about actually configuring your OpenSearch cluster to get started with GPU acceleration. So Navneet mentioned that we are using a remote object store. If you're familiar with OpenSearch, you know that OpenSearch integrates with a lot of remote object stores already. There's the repository interface, which you can use for snapshots. You can use S3, Azure, GCP. You can even bring your own. So we use this same familiar interface. So if you've ever worked with a repository before, you'll know how to set up the object store for the vector transfers. Next, we just set the feature to enabled. We want to set our remote index build service endpoint, like so, and then you're good to go. So we've both now talked a lot about this remote vector index build service. This is probably something new to everyone here. This slide then is to talk about how you can actually go about setting up your own remote vector index build service. So we have a few Docker images available on the OpenSearch Docker Hub that will help you set up and even customize your own remote vector index build service. Here's a QR code for the OpenSearch Docker Hub if you'd like to take a look. So first we have an image that we call the base image. This includes the NVIDIA QVS CAGRA algorithm, includes the FEISS GPU library, and then includes the FEISS bindings. On top of that, we have something called the core image. So this includes the actual vector index builder. This includes the GPU to CPU conversion logic. And then it includes the remote object store interface. So this is what will actually do the download from whatever remote object store you've chosen. Additionally, we also have some more components for memory management and metrics publishing. And then finally, on top of that, we have an API image. So this API image conforms to the API contract that OpenSearch expects for remote vector index building. This architecture is what enables those four things Navneet mentioned earlier. It helps us be hardware agnostic, cloud provider agnostic. It allows you to be multi-tenant, and it allows you to build this in a way that can be done pay-as-you-go. So for example, if you want to bring your own hardware, you don't want to use the NVIDIA QVS algorithm, you can just plug in a separate base image. If you want to use a different cloud provider that isn't supported out of the box, you can plug in your own core image with the customized the customized object store downloaders and uploaders. And then if you want to build this as a multi-tenant service, or if you want to configure pay-as-you-go, you can customize your API layer, or you can customize your metrics publishers for metering. All of three of these images can be used all together, or you can pick whatever you want and deploy it however you like. So the next slide is just some more QR codes about everything that we've talked about. If you want to read more about the official documentation on like all these settings, there's some more expert settings there that I didn't mention here. We have the original performance blog up there. And then we actually have the remote vector index builder GitHub repository, which is what builds those three images I just talked about. If you have any ideas for contributions, please take a look. And then I think we have just two more things. The CAGRA hyperparameter tuning issue that Navneet mentioned earlier. This has like all of the information regarding like how we finally decided what hyperparameters to use. And then finally, just a meta issue for this like entire project. It has basically like all of our ideas from the beginning, and it goes through how we ultimately landed on what we landed on. So I'll pass it back to you, Navneet, for what's next.
Yeah, so thanks, Jay. So let's look forward to what we are going to do next. Okay, by the way, there are some of those ideas present in this meta issue, which talks about, by the way, this meta issue is not only about remote index build acceleration, it's completely about how we want to improve our indexing speed across the board. So just do check this out. In terms of what next, just went too quickly. So the first thing that we want to introduce is GPU accelerated search for our vector component. So right now we've just built the indexing flow. We want to move towards the vector search flow also, because that's one of the logical steps that we can think of. Second is improving the transfer rates from GPU machines back to CPU. So this is also one of the things that we are seeing not as a bottleneck, but an area where we can actually improve. So right now, if you look at, we are actually transferring the whole graph and the raw vectors back to the data nodes. So one of the idea over there is, hey, why don't we just transfer the graph data structure and forget about those raw vectors, because you already have them on the data nodes. So that's the next step. Third thing is, one of the things which Corey was also mentioning is how we can build indices larger than the CPU memory. So right now, as Jay was mentioning, that we have added a setting in which will say that, hey, how much larger index that you can build, and after that we'll just fall back to CPU nodes. So we wanted to basically remove all those thresholds to say that, hey, you can build as large index as possible. This is one of the next steps which we would be targeting in terms of how we can use the how we can use these GPU machines to build indices which are like very large in size. With that, thank you everyone. If you have any questions, we are here to talk about it. Thank you.
Yeah, I think we have a few minutes for questions.
Yeah.
Is this feature already available? And if available, how can we enable this feature?
Okay, that's a good question. So this feature is launched in 3.0 version of OpenSearch as an experimental feature, but right now this feature is fully available as a GA feature in 3.1, and with the recent release of 3.2, we have added the support for not only FP32, but FP16 byte and binary vectors with GPUs. So all the features that you see currently with OpenSearch Vector Engine in terms of like different quantization techniques, all of them are available right now with GPUs. Okay, and in terms of usage, as Jay mentioned, there are these like images and the setup part which he has went through. We have a documentation link, so you can go through that documentation to help you set up. And if you face issues, feel free to cut GitHub issues. There is Slack of OpenSearch, so reach out to us in the hashtag vector search channel. Yeah, yeah.
So the fact that the code can opt out of the GPU either by an error or because the segment is too large, isn't that causing like instability or unexpected spikes based on like the randomness of merges?
Sorry, I didn't understand your question properly. If you can repeat. I understand the larger part, but I didn't understand the smaller part.
You mentioned that the code can choose not to use the GPU accelerated
Yeah.
by either because the segment is too large or because it failed and
Yes.
it goes back to CPU.
Yes.
Isn't that causing like unpredictable spikes?
Yes. Yes, absolutely. I think that's a very valid question. So in terms of like smaller segment builds, it will not create a problem. It's actually beneficial. Now, that's where the second part, if you have uploaded all the vectors to the remote store and then you go to the GPUs and your service fails and you fall back. Or let's say you can think of a case where you have actually built 90% of your index and then it fails because of hardware issues or anything like that. Yes, on those cases, it's bad, okay, because you would be spending time on the GPU side, okay, and then you are falling back to the CPU. Yeah, that's a known limitation from the overall system. But if you look a little bit closely in it, it's let me just answer that question. So if you look a little bit closely, it's not that bad in terms of like, hey, because your GPUs, if you just see in terms of raw performance of GPUs, they give you like 40 to 50x faster index builds. So even if you spend like 5 minutes in an index build which fails, it's not that bad, I would say. And that's where like this is not part of the OpenSearch cluster, so the responsibility lies within the OpenSearch, let's say a provider or the setup to ensure that there's high availability. Okay, and we are also adding few more techniques inside before, like right now we are just looking at segment sizes. We are also trying to add more features to say that, hey, before even uploading the vectors to the GPU, to the remote store, can I check quickly with the remote system to say that, hey, are you up and running, are you green, can I send you those vectors or not? So there are more things that I would say we need to work on, but I hope that answers your question.
Yep.
Yeah.
Hi, I have a question regarding to actually which scenario did this apply small, or is that more for like a batch scenarios where I need to review the full index, or is it also apply to let's say a streaming scenario where we constantly have some data suggestions coming in, and for each cases, I mean for the batch use case, so how do we solve this efficiency problem? Because basically, let's see, we have an index that we review every week, but okay, just one time every week. So how we solve that issue? Of course, I think multi-tenancy will be a solution. And on the streaming case, so how do you make the decision? So okay, at this point, how you build a new index?
Yeah. Got it. That's a good question. Yeah, so in terms of, let me start answering by the bulk case where you are periodically building the indices. In that case, I think it's a no-brainer that you have a full index which is like millions or tens of billions of documents present in it. You want to rebuild it and you want to rebuild it fast. Okay, that case is very straightforward. You use the GPU acceleration. Now the streaming case which you're talking about, let's say if I have a stream of vectors or documents coming into OpenSearch, should I use GPU-based acceleration or not? And that's where if you see the idea that we have added is during the streaming, if your segments are becoming very small, we will not go to GPUs. Okay, we will still do the CPU builds or we will not even build the index. Okay, which was that smarter index builds. But even during the streaming, it can happen that within 1 hour, your more and more segments are getting created which are smaller in size, and then you need to do the merges. And that's where, if you have enabled the GPU acceleration, it will just go ahead, look at the segment size and say that, hey, it's greater than that XMB, let me go to the GPU. So from a streaming case, if you'll say that, hey, I am just ingesting like 100 vectors in like a minute and all, maybe you'll not hit the GPU. But the moment you have more and more vectors coming in, something like, hey, if you have like events or chat events which are getting generated every day, those are the cases. Okay, I think we we need to leave the room.
Yeah.
But yeah, if you have more questions, please feel free to bug us. We are here right outside the room. Okay, I hope that answers your question. But if not, I'm outside. Okay, yeah. With that, thank you.